Okay, we're going to go through another example problem using conservation of momentum. And this is a classic problem. I think there's even a version of it, or even this problem, in your sample problems. But in this problem, we're going to have to use Bernoulli and conservation of momentum to be able to solve it. So for this problem, we have a nozzle that is shooting out some water. And it's shooting it straight up, and it's impacting a plate of mass m. And it's pushing on this plate, and then this plate will basically ride at some equilibrium height h. And what we are to determine is an expression for this equilibrium height h of the plate. Yeah, that's exactly what we're supposed to find. So now, find h. And first, as always, we'll find an expression for it, and then we will evaluate h if m equals 1.5 kilograms. D, the diameter of the nozzle is 2 centimeters. And the velocity at the exit is 10 meters per second. Okay. So now we'll list the assumptions as always. So one, we will assume that the flow in the nozzle and in the free jet and in the region near the plate is steady. So we'll assume steady flow. Two, we will assume incompressible flow. And we'll further assume that the density is constant. Right, because this is a water hose shooting out water, and so we don't expect the density of the water to vary very much. 4, we will neglect viscous effects. Okay, and then we will also assume in the jet a uniform flow. Okay, assumption 6. We will use a stationary, non-deforming CV, and that has the consequence that Vxyz, which is the relative velocity between the fluid and the control volume, is just equal to the fluid velocity. And 7, we will there's a few additional assumptions, but rather than making them up front, I will leave space for them down the road. But I guess there is one more that we can make right away, and that is the impermeable wall on the plate. Okay. Okay, so, and I'll leave some space down here for a few more assumptions that we'll have to make as we go down. But just looking at this problem, we know that we're looking for the equilibrium height of the plate, so we know that the plate is not moving up or down as a function of time, which means that if we take a snapshot of the flow field in the plate, if we take it at, say, 10 different times, we'll get the exact same picture all 10 times. So that means we are our steady flow. It's water, so we can assume it's incompressible. The density is constant. We're neglecting any viscous effects. We don't expect them to be very important for this problem. We're assuming that in the free jet here, the flow at any elevation is uniform. And I'll add that at any elevation. In the free jet. Okay, and yeah, and then we will choose our control volume to be stationary and non-deforming, and I'll get into that later on. And we're also assuming that the water is not going through the plate. Okay, so now for the solution. So for this problem, we need to combine the Bernoulli equation with linear momentum. So let's first just look at the linear momentum equation and start crossing out the terms we don't need, and so we can start simplifying it. Okay, so we have the acceleration of the control volume itself times the mass inside of our control volume, which we need to choose yet, dv plus partial t of the volume integral of rho v xyz dv plus the surface integral of vxyz rho vxyz dot n hat dA is equal to the sum of the forces acting on the control volume. Well, first we're assuming this is a non-accelerating control volume. So this is a stationary CV. So that term goes away. The flow is steady, so we can neglect that term. And we can't get rid of this term, but we can simplify it because we are assuming a stationary control volume. V xyz equals V minus V at the control surface for this integral, and that's just 0, so this just equals V. Okay, and now we need to look at the free body diagram in order to evaluate the sums of all the forces. So now let's do that. So we sort of simplified this about as much as we can to this point, but I will write what it does simplify to. So this implies that for the terms we have left, we have the integral over the control surface, not CV, CS of V rho V dot n hat dA equals the sum of all the forces acting on it, and these include the surface forces, the body forces, and any external forces pushing on our control volume. Okay, so now let's draw our control volume in free body diagram. It seems to be, because we need a control volume to evaluate this piece, and we need a free body diagram to evaluate the sum of all the forces. So let's do that. So we have, for reference, I'll draw, and like I did before, like I would do in dynamics as a student, I would always put the time rate change of momentum on the left side, and I would set that equal to the sum of all the forces. So again, in dynamics, when I was a student, I'd put the accelerations on the left side and the forces on the right side, just to make sure that I didn't get any signs backwards. I was very prone to error when I was a student, and if I put the forces in the acceleration diagram or the forces in the accelerations in the same diagram, I would mess them up all the time, because I would forget that either the sign of the accelerations or the forces should be flipped, and I would always make that mistake. So I would just start doing this. Okay, so now we'll do the control volume portion of this. And what we'll do for the control volume is, since we want to analyze the plate height, what we can do is we can choose a very small control volume that just focuses in on the very end of the free jet, where it's where it is essentially still a free jet, and it's not influenced by the impact point, and we'll follow the edge of the fluid. And the reason we'll follow the very edge of the fluid is so that we know that we're following that streamline, and there's no mass that crosses a streamline. Then we'll go up over here, follow the bottom of the plate, come around back down, and then go to here. And so And so that's what I'll choose to be the control volume. The other way that you could solve this problem is you could do the control volume around the entire mass of the water, but that gets pretty complicated, and I'll explain that in a little bit. Okay, so we'll do the control volume first. So we have the plate. I just like to draw that for reference. And we're zooming in close to the plate, so the jet would look something like this. And we'll choose the control volume to, we'll make a cut at height h. And we'll follow the edge of the water and go up straight, and then go just underneath the plate. So there's our control volume. Now, what we have in this control volume here is we are following the edge of the water. This is following that streamline, so the curve follows the streamline. And it's the outermost streamline, so it's the very edge of the jet. And what this means is that v dot n hat is equal to 0. Okay, which means that there's no mass, there's no material crossing this area over here. And then we have the flow coming in here at some velocity. I'll just call that vh, and that would be going in the j hat direction. Okay, and n hat would point down, so n hat would be minus j hat over here, and we'll have some v at the sides. Okay, and then we'll also be going equal and opposite in both directions. Okay, so that's what our control volume looks like. And now we need to do the free body diagram. So I'll just draw the control volume itself, and now this is the free body diagram on the control volume itself. Okay, so I have a force on the top of the plate from the weight of the plate. So that would be a mass times gravity, and I have weight from the fluid. And we are going to assume that since this control volume is zoomed in on a very small portion, we will assume that W fluid is small. And that's just due to our choice of the control volume. Okay, so we don't need to worry about that. Okay, and then we also have and actually what I will do, I'll actually redraw the control volume, and I'll have it cut through the top of the flat plate. Okay, it doesn't change anything, but it does make something a little more straightforward that I'll get to in a minute. It's something I just realized. I've given this example about 3 times, and it's something that I've just realized. Okay, so it contains the plate, and so there is still a mass times gravity from the weight of the plate. And that is now inside of the control volume. Okay, and so then we also have pressure pushing on all of these sides. Okay, and then this is PATM that is pushing on all the sides. And now what this choice of the control volume here, when I extended it up a bit, is that I know what the pressure is over here, but I don't know what it is underneath here. So I don't know what that pressure is. Okay, and so this problem becomes a bit more straightforward if we just choose the control volume to be on the top, because we know what to do with that pressure. Okay? And so then, because we're assuming that the weight of the fluid is small, I'm just going to basically cancel that out, and I'm not going to worry about it. And then furthermore, the sum of all the pressure forces is equal to minus the surface integral of P n hat dA. And we know that that it's still a free jet here. This control, and so it's a free jet. It's not a free jet here, but the control surface is just on the outer edge of the surface, so we would expect the fluid there to be at atmospheric pressure, and then the plate is turning the flow, and it is exiting also as free jets. So the pressure here is atmospheric pressure, the pressure here is atmospheric pressure, and the pressure on that surface is atmospheric pressure. So the pressure is uniformly everywhere atmospheric pressure pushing on this. Okay, so this equals minus the integral of the control surface of PATM n hat dA. And as I argued before, since PATM is constant, we can just cross that out. And the reason we can do that is we can use the gradient theorem. So the integral over the control surface of PATM n hat dA, we can use the gradient theorem and convert that to a volume integral. So that's the integral over the control volume of grad PATM dV, and that's integrated inside of the control volume, but PATM is constant, so its gradient is 0. Okay, and so because we have uniform pressure acting on all sides of this control volume, there's no net pressure forces that we need to worry about. So the only important force in the control volume we need to worry about is the body force of the plate itself, and that's it. So that's just mg. That is the only force that survives. Okay? So now, we can now go and evaluate all the terms. So we know then that the sum of the forces equals minus mg j hat. That is the only term that survives. And now, we can now form this integral there. Okay? And so we want to form this. We have the integral over the control surface of V, rho V dot n hat dA. And that is equal to the integral over, I'll call this surface 1, the sides here surface 2, the top surface 3, and the curvy side surface 4. Okay? And so we just break this into the four pieces. We have the integral of A1 of V1 rho 1 V1 dot n hat dA1 plus the sides, the integral over A2 V2 rho 2 V2 dot n hat 2 dA2 plus the top, the integral A3, and I will just become lazy and just not write that portion out, and we got to add the curvy sides, and the same thing. Okay, so we can start crossing out terms now. A3, well, A3 is above the flat plate. There simply isn't any flow there. There isn't any water there. So we can cross that out. So there's no flow, no water. Right? Because we chose it to be above the flat plate, and there's no water going through the flat plate. And so we can cross it out due to an impermeable plate, because there's nothing on the other side of it. And we need to be a little bit careful with area 2. but I will show, and I'll prove this in a minute, that this term is also 0, but I would expect you to show, to make the argument that this is 0. And then A4, we've chosen the control volume to follow the edge of the jet, so V dot n hat equals 0 on outer streamline. So that goes away. So now we will work with these two. We will work with these two areas here. And again, this one just goes to 0, but I need to show you how. So area 1. That's where the jet comes in. So I'll just draw that surface here, just for reference. We have some velocity, v1, coming up, and that's going in the j hat direction, and its n hat is going down, n hat 1 equals minus j hat. Okay, so we want to form this integral, but first let's just start forming our pieces here. So we have v1 equals v1 j hat. We need to find that. We know that n hat 1 equals minus j hat. Then v1 dot n hat 1 equals this dotted with this, and that just equals minus v1. Okay. So then v1 rho v1 dot n hat 1 equals a v1 j hat times rho times v1 dot n hat 1, which is minus v1. Oops, that looks like it's minus v1. Let's say times minus v1. Okay, so that's what this turns into. Okay, so now I want to form the integral over a1 of this. So the integral over a1 of v1 rho 1 v1 dot n hat 1 dA1. Actually got a little bit sloppy here. That equals the integral over the area of minus v1 j hat times rho of the water, and that's constant, so I'm just going to call that rho, times v1 dA1. We are assuming that the flow is uniform at any elevation in the free jet, so I can take these terms here and pull them outside of the integral. So this equals minus v1 j hat times rho v1, and that's times the integral of a1 dA1, and that's just the area of the jet. And so this entire integral here becomes minus v1 j hat times rho v1 times the area. And then what is the density? If we have a uniform flow, what is the density times the velocity times an area? That's just m dot of the jet. Okay, so that is the mass flow rate. So this equals minus v1 j hat times the m dot of the jet, and I'll write it a little bit differently. Minus v1 times the mass flow rate of the jet times j hat. Okay, so we have this integral here. It became fairly straightforward. So again, this nasty surface, this nasty like integral here, just turned into a fairly simple form. And as you guys get experience doing this, you will be able to more or less in your head go from here to here. But in the purposes of class, for the purposes of learning, I expect you to go through all of these steps because the very common mistakes are that the velocity vector and n hat are incorrect. Then you just make mistakes forming the integral itself. Okay, now we need to make a statement about area 2. Okay, area 2 encompasses both of the flows leaving the site. So we can break n hat 2 into two pieces. We'll have n hat, and I'll call that 2a equals, say, I hat, and we'll have v 2a equals some v2 I hat. And we have this piece over here, I'll call that 2b. So n hat 2b equals minus I hat, and v 2b equals some v2 I hat, but in the minus direction. Okay? And so another implicit assumption that we're making here, and I need to put this to the top, is that we're assuming that the flow is symmetric. Okay? That is, we have the exact same picture over here as we do over here. It's just that the velocity is flipped. So we could say that at an eighth assumption that the flow is symmetric. Actually, axisymmetric would be the correct word. Okay. So now, what that means is that we could do that the integral of a2 of the v rho v dot n hat dA, that's equal to the sum of both of these pieces here. So that's the integral over a2 a v rho v dot n hat dA plus the integral over a2b v rho v dot n hat dA. Well, here we could say that v dot n hat, if you evaluate that for both sides, that's just v2 for both, positive v2. But here, for a2b, v2b equals minus v I hat, and here v2a equals v I hat. So what we'll wind up with here then in these integrals is we'll have the integral over a2a of minus I hat v squared rho dA. Oops, and this is a2a, and that should be positive, not negative. Sorry about that. Plus the integral over this piece here, the integral over a2b, and that'd be minus I hat v squared rho dA. Okay, and I just basically substituted just substituted everything in. Well, we can factor out this negative sign here, and you can see that we have the exact same integral here because we're assuming that the flow is symmetric, which means the area here is the same as the area here. So these cancel out, so this whole thing just equals 0. Okay, and so in your homework, you can just note that it's symmetric, so you can cancel out those side effects. You don't need to go through this long proof to basically argue it, so you can just say symmetric. Okay, so that goes away. So there's no net force. So the only piece to the surface integral is just this piece over area 1, which we already did. Okay, so now we can put everything together. We have the surface integral of v rho v dot n hat dA is equal to the sum of the forces. And so that rho v dot n hat dA, that was minus m dot in the jet. I believe I called that m dot jet v1 j hat, and that's equal to minus the mass times the gravity of the plate. So that's just the weight of the plate. Okay, so now this is just a relationship here. So we'll just have m dot of the jet V1 is equal to the mass times gravity of the plate. So far that's all we can do. Now we are asked to find the plate height, and there's no obvious plate height here. So what do we do about that? Well, we do have a free jet that's going straight up. Okay, so the fluid particles that exit the nozzle have to travel up to meet the bottom, or to meet the bottom of our control volume. Okay, and so we're assuming that this distance here is quite small, so we can evaluate the height, the velocity of the water at the free jet. So we do need the velocity at the bottom of this free jet, but as or at the bottom of the control volume, but as the water flows up through the jet, it's still going to decelerate because it needs to fight the gravity. So in other words, the Bernoulli equation, we do meet the steady flow, constant density, negligible viscosity, and we can easily consider a streamline from the bottom of the jet to the bottom, up to the entrance of our control volume here. Okay, now there's another assumption here. We're assuming that our control volume cuts this something like this, and we don't know this distance here, L. We do not know that. So essentially we will assume also then that the size of the control volume, the size of this control volume is small. This is the assumption that allowed us to neglect the weight of the water in the control volume. And this also means that even though we are technically evaluating the velocity going into the control volume, and we're using Bernoulli to do that, we can treat this height here as just h. Okay, even though it is down just a tiny bit, we are assuming that the amount that it is shifted down from h is very small, and we just don't need to worry about it. Okay. So we'll apply Bernoulli between those 2 points. Okay, so apply Bernoulli. Okay, so we have 1/2 v squared at the jet plus g plus 1/2. Let me write it the normal way. 1/2 rho v squared plus rho g z plus p, and this is at the jet. I'll put this at, I won't call this 1, I'll call this E for the exit. E. Okay, and E stands for the exit velocity of the jet, and this is equal to 1/2 rho v1 squared. This is our state 1 in the control volume, plus rho g z1 plus p1. Well, and I'll just draw the little free jet here. This height here is h. Okay, this is a free jet. So in the free jet, P equals PATM. Okay, and because the pressure is the same on both sides, that basically all these pressure terms cancel out, so we don't care about those. This here is the exit velocity of the jet, we know that, and I'm going to choose my datum to be on the very bottom. So here, this term cancels out because it's at the datum. Okay, and this height here, which is state 1, this height there is just our unknown h. Okay, so we want to find h, and we have up here conservation of momentum in terms of v1. So we'll solve this for v1 and substitute it into conservation of momentum. Okay, So we have that v1 squared equals, and all the densities cancel out actually, you don't need to worry about them, that v1 squared equals ve squared, which is the exit velocity of the jet, minus gh. Okay. Oh, minus 2gh. Okay, so we can then say that v1 equals square root of ve squared minus 2gh, and we can take this expression here and substitute it into there, and we have that m dot of the jet times square root of ve squared minus 2gh equals mg. So then we can solve for h, and also we can just note that m dot jet equals rho times the exit velocity of the jet times the cross-sectional area of the jet, so that's pi over 4 d squared. So then we have this expression here for h in terms of everything. Solve for h. I'm not going to go through the steps here. And you'll find that h equals 1 over 2 times the gravity times ve squared minus the quantity 4 mg over pi rho d squared ve, this whole quantity squared, and close the bracket. And so that is what h becomes if you solve it properly. Okay. Then if you stick in the numbers, you will find, and I would expect you to show this explicitly, but if you stick in the numbers, you'll find that h equals 3.978 meters. And as always, I expect you to show all of the unit cancellations and everything, but in the interest of time for this example, I won't do that.